Related rates, big, important section. Read the problem from the Osterby-Zorn calculus handout about getting a traffic ticket. That is on the previous page. Note the Pythagorean theorem application and the implicit differentiation. Also note that values were given in the problem that are not substituted into the problem until it has been differentiated. That is the key right there. So far, we have used the derivative mainly as the slope of a tangent line. Instead of having delta y over delta x, we might consider the change in position over the change in time, delta s over delta t. For example, that would be your average rate of change. If I travel 300 miles in 6 hours, you would say that my average velocity or speed or rate is 50 miles per hour. But if we put this through a limiting process as delta t goes to 0, we will have ds dt, which is our instantaneous rate of change. And that is what we're going to talk about now. We first have to get comfortable with this notation. Notice that to get to an instantaneous rate of change, we are often taking the derivative with respect to time. So first, we're going to translate a few sentences using proper calculus notation. Here's our first sentence. The area of a circle is increasing at a rate of 6 square inches per minute. Area is usually denoted with a capital A, and so dA dt equals 6 square inches per minute. The volume of a cone is decreasing at a rate of 2 cubic feet per second. Volume, dV dt, the change of volume with respect to time. Decreasing, negative, 2 cubic feet per second. Note the units, they matter. Population of critters at WHS, you have to change that, is growing at a rate of 3 critters per day out there in that prairie. dPdt equals 3 critters per day. The height of a tree is increasing at the rate of 1/2 foot per year. dHdt, h little h stands for height most of the time. Increasing at 1/2 foot per year, so 0.5 feet per year. You could have written 6 inches per year as well. The water level in my fish tank is decreasing at a rate of 2 inches per hour. dHdt, that's going to be the height, is negative 2 inches per hour. Notice that if something is decreasing, it's expressed as a negative rate of change. If something is increasing, it is expressed as a positive rate of change. So in these next 5 problems, take a minute and try to write out, you have the notation, try to write out or describe, like we had up here, what is going on. Capital C stands for circumference, capital S, surface area, R, radius. So pause and try it. The circumference is increasing 2 inches a day. The surface area is increasing 5 square yards per minute. The area is decreasing 4 square feet per second. The radius is increasing 40 centimeters per minute. The volume is decreasing 10 cubic meters per second. Note that the units will be very important with this topic. From now on, when I refer to a rate of change, you should automatically assume that we are talking about an instantaneous rate of change. In other words, a derivative, which is an instantaneous rate of change. If I mean an average rate of change, I will specify that. And this is very fun. We are going to complete this page. So I'm just going to go through a couple of these with you, but you need to recognize these formulas and be able to state what they are and to find their derivative. You don't need to memorize their derivative, you need to be able to find it. So let's look at this first one. Area is pi r squared. We remember that pi is a constant. and we're going to take the derivative with respect to time. dA with respect to time, dA dt. That's chain rule. Because a is to the first power, this is actually a to the first power, and we're going to take the derivative of it with respect to time. And we're going to take the derivative with respect to time of pi r squared. The derivative of a with respect to time, the 1 comes down, a to the 0, chain rule, dA dt. So that's where our dA dt comes from. Equals, pi is a constant, but the 2 is going to come down for, so we have our pi. The 2 is going to make it 2r to the first power, chain rule, times dr dt. So the clean version of that is dA dt equals 2 pi r times dr dt. And what differentiation rule do we use? We just used constant multiple. There's our constant. Let's look at volume. Now I have a product rule going on here because I'm multiplying r squared times h. So let us remember, we're going to take the derivative, dv dt, equals pi is a constant, and r squared times dh dt plus 2r dr dt times dh. Okay, it's ugly. But what's really neat about this is when you get your derivative into this form and you're working a word problem, that's a lot of letters there, but you're looking for one thing. And that means that for everything you have in this equation, you know everything but the one thing you're looking for. So that's going to be interesting. All right, this is a squared plus b squared is c squared. That's Pythagorean theorem. Again, chain rule, 2a dA dt plus 2b dB dt equals 2c dc dt. Notice that all terms are divisible by 2, so why not simplify that? So I leave the rest to you. Notice here we have a product. Here we don't. Here we have a product, number 8. Okay. Down here on number 17, we have a product. Okay. So you want to get that done. And I have a solution page you'll be able to check your work on. Notice I might have an evaluative exercise in the next class to see if you have some of these correct before I show answers. Draw a picture of the situation described in the problem. That is the first thing you're going to do. Make a list of all the given information and of the required quantities. I always write, what do we know? What do we want? Label each quantity that varies with time with an appropriate variable, and each quantity that does not vary with its constant value. Relate the variables in an equation. Check to see that all necessary values are accounted for. Differentiate the equation with respect to time. That would be your implicit differentiation using chain rule. Substitute the known quantities into the result of step 6 and solve for the unknown quantity. Note, very important, you do not substitute quantities which represent change. In other words, things that might be changing, like the radius of an ice cream cone sphere. As the ice cream is melting, the radius of that sphere is going to change. So you do not substitute quantities which represent change until you have written an equation which represents change. In other words, the derivative. Incorrect things students do when solving related rate problems. Now, it would be presumptuous to suppose that one could ever list all of the things they do, but here's the main ones. They don't read the problem. It's a word problem generally, and most times people do not like to read them. They assume relationships that are not valid. They substitute non-constant quantities before differentiating. This is the biggest error. They substitute numbers in the wrong places. They argue the appropriateness of the problem instead of just doing it. That couldn't happen. They forget the product rule. That is major. They omit the chain rule. That's another very big mistake. And they just omit the problem altogether. Now, you wouldn't do that, would you? All right, related rates. Related rates is a fundamental topic in calculus and should be one you do everything in your power to understand. In essence, it is one of the major reasons that calculus was developed because it studies and analyzes rates of change of objects as they change with respect to each other and with respect to time. Here are two worked problems. The volume of a scoop of ice cream is decreasing at a rate of 2 cubic millimeters per second. At what rate is the radius of the scoop changing when its diameter is 60 millimeters? Now we want to write down information that we know. We know dV dt is negative 2 cubic millimeters per second. Our ice cream is melting. We know our diameter is 60 millimeters, but we know that volume of a cone is going to be 4/3 pi radius squared. So we know that our diameter is equal to twice the radius, so our radius is 30. Now we're going to determine the formula for the problem. Volume is 4/3 pi r cubed. What we know is we know 60, we know dV dt, and what we want is dr dt. So differentiating this, taking the derivative with respect to time, this is 4. The derivative of r cubed is 3r squared. So the 3's are going to cancel, and it's going to leave the r squared, and the rest of that derivative is times dr dt, and don't forget pi is a constant. So what we know in this problem is we know our volume is here, so that is going to be a negative 2. We know the radius is 30, so that's going to go here, and guess what? We have filled in all the variables except for the one we're looking for. So this leaves us negative 1 over 1800 pi is our rate that the radius is decreasing. Negative 1 over 1800 pi millimeters per second. Notice that radius is a linear measurement, so the unit millimeters to the first power. And that would be about 0.00018 millimeters per second. It's not going to last too many minutes because, of course, we're going to eat it. An airplane is flying 600 miles an hour on a horizontal path that will take it directly over an observer. Usually when we talk about a horizontal direction, we call that our x. The airplane is 7 miles high. We are going to assume ideal conditions here that the airplane is staying 7 miles high. So that is going to be a fixed constant for now. Write an equation for the rate of change of the line of sight distance z between the observer, here's my little person who sees the airplane and is flying over, okay, between the observer and the airplane in terms of horizontal displacement x from the observer to the plane, okay? So my line of sight distance is z. My horizontal displacement is x, right? We know dx dt. dx dt is negative 600 miles per hour. Why negative? Because the plane is coming this way. That distance is decreasing. And we want dz dt. Now, what we're looking at here is a right triangle. And we're looking at a right triangle where this side is changing, but this side is not. So we're going to first of all set up our equation. Okay, z squared is x squared plus 7 squared. I can substitute the 7 in because that is not changing. And I can find the derivative of it. 2z dz dt equals 2x dx dt plus derivative of 7 squared is 0. And I am solving for dz dt. So I'm going to write this equation solving for dz dt. Notice that the 2's are going to cancel, and there it is. Now, that is my equation relating z to x. But I know that z squared is x squared plus 7 squared, so z would be the square root of all of that. And by the way, the square root of x squared plus 49 is not x plus 7. Ah! That is a kill me now moment. You wonder what a kill me now is. That's one of them right there. But anyway, I can substitute this in right here for z right there. And there is my equation. And I can now, I have my negative 600. I'm substituting for dx dt. So there we have it. Now I can ask, how fast is that distance changing when x is 10 miles? Now I can ask, how fast is z changing when x is 10 miles? Substitute 10 in here, and I get negative 491.54 miles per hour. When this plane is 10 miles out, when that length is 10, this distance is changing at a rate of, decreasing at a rate of 491 miles per hour, 491.54. And our units matter. That's a very important thing to note. How about when x is negative 5 miles? What does negative 5 miles mean? Negative 5 miles means, here's the person, the plane has now passed me overhead and is now going that direction. So wouldn't it make sense, as the plane is flying this way, for this distance to be increasing? And when we substitute negative 5 in there, I get a positive number for my line of sight distance changing. The plane is moving farther away. We are now going to work two problems. Okay, a 6-foot man is running away from the base of a street light that is 15 feet high. Here's my street light. Here's my 6-foot man. Here he is running away. If he moves at the rate of 18 feet per second, how fast is the length of his shadow? So think about it. The shadow's down here, right? How fast is the length of his shadow changing? Now let's let x be the distance the man is from the base of the streetlight, and let y be the length of the man's shadow. Well, first of all, how could I relate x and y? Do you see the similar triangles hiding in this picture? And in similar triangles, you learned that 6 to 15 would equal y to the whole thing, x plus y. So similar triangles are going to be a pretty important idea here. That's one way to think about this problem. So let's write down what we know and what we want. Again, that's what I always emphasize first. What do we know? We know that the height of the light is 15 feet. We know that the man, point N, is 6 feet. And we know that he is running away or walking away from the light post at a rate of 18 feet per second. That would be this dx dt. And we want the length of the shadow, how that is changing, dy dt. Now, one would think that ought to be increasing. If you think about walking away from a street light, you notice that that shadow gets longer. So we do expect a positive answer for dy dt, just thinking about it. So now we need to set up an equation that will relate these rates. We know that 6 to 15 equals y to the whole thing, x plus y. In other words, small to big equals small to big. Okay, and we can simplify that to be 2/5 equals y over x plus y. And I could multiply both sides by 5 and multiply both sides by x plus y. A lot of you like to call that cross multiply. And I can actually relate y to x. That's what we're looking for. We are looking for an equation that relates y to x, so we can take the derivative of it. So relating y to x, now I have that, and now I can take the derivative of this equation with respect to time. So dy dt for this equals 2/3 is a constant times dx dt. Substitute in what we know, and there we have it. Now, what did we expect? We expect that shadow to be getting longer, and it is. The shadow is lengthening at 12 feet per second. All right, let's do one more. A cube of ice is melting. The side S of the cube is decreasing at a constant rate of 2 inches per minute. How fast is the volume V decreasing when the side is 3 inches? So I like to draw a picture. We know, there's my cube, ds dt is decreasing, negative 2 inches per minute. It's a big old block of ice, right? The volume of a cube is side cubed. What is it that we want? How fast is the volume decreasing? So we want dv dt at the instant, this is why it's instantaneous velocity, at the instant when s is 3. So we're going to start with our equation that relates to two things we're going to need to know about. And we are ready to take the derivative. Taking the derivative, dv dt equals 3s squared times ds dt. Now I can substitute the values I know. I know that s is 3. I know ds dt is -2. 3 squared is 9. Times 3 is 27. This gives me inches squared. This gives me inches here, which is going to give me cubic inches per minute. My volume is decreasing at 54 cubic inches per minute. So when you start on this homework, you will notice that I have given you the answers to each one of them so you will know if you've done the right thing. So your TPs are going to actually come from the lecture manual, page 42A and B, 1, 2, 3, and 8, and then one problem, number 1, out of the textbook. See you next time.